All right, so coming in with our last notes or last video for these notes. I'm not sure if you guys did this part in Algebra 2. So basically what I want to do is a little preview of a theorem that's used in calculus. All right, so let's take a look at our function. We're still using the one that we had, which is the 2x cubed minus x squared minus 4x plus 3. And so kind of taking a look at that function, we want to investigate this a little bit more numerically. Now, what I mean by that is assume that we don't know this, okay? We have no idea what the graph looks like. Assume that we do not know, shoot, I'm having syncing pages problems again. It says I'm synced. There we go. That basically, as we are looking at it, let me just move myself over here, that we don't know what the graph looks like. We don't know anything about the type of zeros that we have. Basically, we're just investigating a function. We have a formula, and we can plug and chug. So if we come in and we just do some basic plugging and chugging, and I'll leave it to you to actually verify this, but if you were to plug -2 into the function, you should get -9. If you were to plug -1 into the function, you would get 4. And going ahead and plugging in, or 0 is easy. H of 0 is going to be 3, and H of 2 is going to be 7. So I'll let you guys verify that in terms of getting those values. Now, the other thing that we want to take a look at is like, what does that actually tell me about this function? And so from the graph, clearly, if I look at the graph, h of x has a 0 between -2 and -1. That's fairly obvious as we are looking right here in the graph. Now, when I find the values of h of -2, which is -9, and I find the value of h of -1, which is 4, how does that guarantee, or what does that say to you about whether or not there's a 0 in between -2 and -1? What about that reminds us of what we did earlier in this problem? So what I would say in terms of that is that what you're seeing here is that there was a sign change between h of -2 and h of -1. And the fact that there was a sign change is what's going to tell me that there must be, I don't know exactly where the 0 is in between -2 and -1, but it does tell me that there is definitely a 0 there. So sign change between, I'm waiting for my computer to catch up here. H of -2 and h of -1 means a 0. And I might want to say, instead of saying a 0, I might want to say at least 1 0, because we don't know what really happens in between if we only have 2 single values. So at least 1 0 exists between x equal to -2 and x equal to -1. All right, so taking a look at this, and I need to like strengthen this statement just a little bit, that we're kind of assuming something about this function that is very, very important. That this at least 1 0 between -2 and -1, that really that's only provided that our function h of x is continuous, that it has to have no gaps or holes or breaks or anything like that. Because if it had a jump, we could clearly be below and then above and not even cross the x-axis. So we definitely need this idea that h of x is continuous. And so with that sign change, when you know that because h of -2 was -9, that tells us that the function was below the x-axis. When h of -1 was 4, that tells us that the function was above the x-axis. And if the function is continuous, then pretty much the only way to get from below to above, if the function is continuous, is going to be to cross the x-axis. Now, we don't know how many times it crosses the x-axis because we don't have that level of detail. If we only have values at -2 and -1, it could cross, 3 times in between. We don't know that. But what we do know, and that's why we're using the words at least 1 0, that is going to be there, as opposed to saying that only 1 0. See, this is not strong enough to say only one, but it is strong enough to say at least one. Okay. Now, taking a look at the next question, it says, does the same reasoning that you described concerning the 0 between x equals -2 and x equals -1 apply and hold true for the existence of a 0 between 0 and 2? Now, obviously, from the graph, we know that we had it there. But the problem that we have is that we do not have a sign change. All right, so no sign change. And basically all that means is that there is no evidence, of a 0. Notice that I am not saying that there is no 0. That's different than this. I'm not proving that there's not a 0 if there's no sign change. I'm saying that I don't have any evidence to support that there is. There may or may not be a sign change. Or sorry, there may or may not be a 0. I don't have enough information, not enough info to tell, not enough info to tell. Let me pause this so it catches. All right, so what I did, I went ahead and pre-wrote a couple of extra things here that I wanted to talk about. And that's, my computer's lagging. I really just want to get this video done for today so that I can have a little bit of a break this weekend. So looking at this, we have that if there is a sign change, so if one y value is positive and one y value is negative, or vice versa, it doesn't really matter what order, there just has to be a sign change on a continuous function that guarantees the existence of at least 1 0. Maybe more, but it guarantees that there's one. If there's no sign change, what that means is that we don't really have evidence whether there is or there isn't. It's not enough information to tell. So we usually say that does not guarantee the existence of a 0, but the 0 is still possible. It just may be that we're just too zoomed out on the graph. Like, for example, like on this one, because it was a double 0, when we looked at it, clearly there was no sign change. But, I could also play around with different things. That what if the function, like if I picked between like the value of h of -1 and the value of h of 0, that one doesn't have a 0 in between it. But again, see how I couldn't tell the difference between just the fact that I got two that were the same sign is not going to be enough to tell me whether or not I switched or not. And if you see one, like for example, if one goes up and down quite a bit, let's go back to this one right here, the one that's h of x. Suppose I told you that we found like h of -3, which is 4, and then I found h of 4, which is -4, and you're like, hey, there's 1 0 in between there. Well, there's actually two. That's the whole at least one that's there. If there's a sign change, depending on where you're picking it, you know that there's at least 1 0, and in this case, there were actually two. So that's, I just wanted you to kind of see a little bit of that as you're looking at it. Now, this kind of idea that if you have a continuous function, you are able to prove the existence of a 0 is something that is related to a theorem in calculus. Let's kind of wrap up what we're doing here in Algebra 2, and then I'm going to talk a little bit about what the calculus theorem is and show you some information on that. So based on what we've seen, what inference can we make about the existence of a 0? So the first fact, all of this is hinging on the fact that polynomials are continuous. This is going to kind of fail if you have a non-continuous function. But if you have a continuous function, no holes, no gaps, no breaks, no vertical asymptotes or anything like that, that if you can find two y values that are of opposite signs, then a 0 of odd multiplicity has to exist on the interval a to b. So there has to be a 0 there. It had to cross the x-axis. That's what this theorem is basically guaranteeing, that there's an existence of a place where you crossed the x-axis because the function was continuous. And hopefully you see why continuity is a requirement for this. And then the second thing is if your two y values, f of a and f of b, if they have the same sign, then there's no direct evidence that a 0 is there or not. It may exist, it may not. It could have cross a couple of times, it could cross or touch and bounce, or it could not have a 0. We simply don't know. That's the not enough information to tell. Now, I did add over here into the OneNote notebook, and let me move myself again over here. So if I am looking at this over here, I added a file. If you're at more on the intermediate value theorem. So I put that in there, and that's mostly for those of you that are going on to calculus. So if you're going on to AB Calc next year, I would highly suggest that you read this document, which kind of gives you this idea of the theorem that this is all based on. Is something called the intermediate value theorem. Intermediate means in between, and that's kind of what we're looking at. And we're using it in terms of finding zeros, and that's what we did in Algebra 2. But here in this one, kind of the briefly non-mathy way of saying this is saying that if I have two y values, one larger than the other, doesn't matter if it's this way or this way, left or right, doesn't matter, that if there's no holes, rips, gaps, tears, asymptotes, or anything in the middle, if the function is continuous, then get from this y value down here to this y value up here, I have to travel through every possible y value in the middle. That there has to be the existence that the function value has to have take on every y value from the min to the max of that interval. And that's basically all it says. More mathematically stated, as you go back and look at this, the intermediate value theorem basically says that if you have a function continuous on a closed interval, then, and you have a value, a y value, they're calling it c in this. I think in calculus we call it k, but it doesn't really matter. We have a constant that is a y value. And if it's a y value that's in between the beginning of the endpoint to the end of the endpoint, that the function has to intersect that y value somewhere in between. Now, the c that we were using in Algebra 2 is the 0, because we're trying to prove that there is an x-intercept or a 0, or that we cross the x-axis. In the more general terms, what this is talking about is that what you're doing is you're crossing the horizontal line y equal to c at some point to get from, if you have a f of a down here, f of b up here, and there's a line x equal to c in the middle, to get from here to here without, when in a continuous function, you have to cross that line in order to get there. That's basically all it says. So I put this in the folder for you, so that way, if you're going to calculus, I highly suggest that you read that. All right, let's go back to where we are here in Algebra 2. All right, so let's have you guys take a look at this next kind of idea. This is kind of applying this idea of this theorem to it. So what I would like you to do is go ahead and look at the problem and see if you can answer these three questions. And then come back and then we'll kind of discuss it, and then we'll be done with this set of notes and you can work on the worksheet. All right, wrapping up this set of notes, f of 1 equals 0, so x equals 1 is 0. And since the degree is 4, and we already know we have 3 zeros, I know there are no complex because those occur in pairs, if you didn't remember that. There are 2 sign changes shown above in the graph, and so those each have to be a multiplicity of 1 because they can't be 3, because then it would add up to be more than the 4. And so that adds that in. And then for the last 2, between the values, I wrote up what we would kind of write it up the way in calculus for a positive and a negative, showing a sign change, and then showing there exists a 0 in between. So take a look at that, make sure you get your notes down, read the intermediate value theorem, try the worksheet, and that will wrap up the videos for today.